In this example, we're going to use triple integrals to find the volume of a very well-known solid, just to practice setting it up and on something that we have a good idea about what the answer is going to be. So I have this equation. This is x squared plus y squared plus z squared equals 4. And that's well known that that is a sphere of radius 2. And if you go and you think about the volume of a sphere, it's 4/3 pi r cubed. In this case, r is 2. R cubed is 8. So that's 32/3 pi. So that's the way we're going to, if we get that answer, we can be reasonably sure that we've done this correctly. So we want to say, okay, well, how can we do this using the idea of a triple integral? Well, if we need to set up those equations, one where x goes from a constant to a constant, one where y is a function of x with lower upper bounds, and another where z is a function of both x and y. So this is a sphere, and there's another piece that we want to say. I apologize. Since it's a sphere, we know that in each octant, so just like a standard 2D has quadrants, in 3D you have octants, where you have 8 different ways that you can slice up the coordinate system. And since a sphere is the same in all 8 octants, right, it has the same volume in all 8 octants, we can just look at the first octant and then we can multiply our answer times 8. And that'll save us some time. So let's go ahead and annotate that a little bit. We'll notice that since we're only considering, this region here. Now for x, y, and z, it looks like x goes from 0 to 2. And then that looks like a quarter circle. So we have to say that y goes from whatever x, or it goes from 0 to some sort of bounding curve up here. But we also know that the projection of the sphere onto the xy plane is just a circle, right? If we sliced it in that cross section, it would be a circle. So let's think about the case where z equals 0, right? That's the xy plane, z equals 0. So then, if z is equal to 0, then this is just the equation of a circle, x squared plus y squared equals 4. So that tells me that y goes from 0 to the square root of 4 minus x squared, which makes sense because if x is 2, which is all the way out here, then y is stuck. If x was, let's say, like 1, right? X is 1, y goes all the way out here to the square root of 3. So it kind of makes sense, kind of satisfies the internal litmus test. And finally, we need to figure out what z is. Well, in this particular case, it looks like z starts at 0 in the xy plane and goes all the way up to, we can use this. If we solve this for z, we move all the other pieces over here and then take the square root. Minus x squared minus y squared. And, you normally have to worry about that sort of plus or minus, whether or not it's one or the other. Well, in this particular case, we know that we're dealing with the positive values of z. So we're dealing with the plus version here. And this sets up some kind of nice limits because you're only dealing in very, very simplistic forms. Everything starts at 0 and goes up. So let's go ahead and set this integral up and start going through it. First thing is 0 to 2, 0 to 4 minus x squared, and 0 to the square root of 4 minus x squared minus y squared. And that's going to be dz, dy, dx. So again, remember, we don't have to use dv here because now that we've defined the limits for volume, we can use an iterated integral. And for volume integrals, the function, that sort of f of x, y, z, is always just 1. So when we take the antiderivative, you're really just going to get z, and then you're just going to plug in that. So you're really just stuck with 0 to 2, 0 to 4 minus x squared of square root of 4 minus x squared minus y squared dy dx. Now this one's a little tricky. So I'm going to go ahead and pull my my cheat sheet here because, and that reminds me, remember when we're integrating this, we have that 8 in the front because it's 8 times this. So it's 8 times that. And they have this. This is kind of nasty. So I'm going to go ahead and integrate this for us. So what you have to do in this case is you have to do, I'm not going to call it a trick because it's really not a trick. But what you're going to do is you're going to define a constant. So instead of 4 minus x squared, you're going to say something like this. You're going to say a is the square root of 4 minus x squared. So a squared is 4 minus x squared. And what that does is you go up here and that gives you a squared minus x squared dy dx with the the double integrals. And you want to do that because this is sort of this is like something you look up in a table. And when you look it up in the table, it'll be in terms of a, and then you'll be able to plug back in all the values of a here. And I'm going to skip some of the particulars because what ends up happening is you have to do a trig substitution, and then once you do the trig substitution, you're going to have to plug back in for a. So I don't want to waste too much time going through that, but it's a standard trig substitution. I do kind of recommend you go through it on your own time because it's good practice. But what you end up with is 8, the integral from 0 to 2 of 1/2 4 minus x squared arc sine of y over the square root of 4 minus x squared plus y times the square root of 4 minus x squared minus y squared from 0 to 4 minus x squared dx. Okay, so you end up with that thing, and it ends up being, for a couple reasons, you do a trig sub, but you're going to end up with like a cosine squared, which you have to convert into 1 plus cosine 2 theta. So one of them comes out as a theta, and one of them comes out as like a trigonometric function. So the trig function comes out as this, but the other one, since it's in terms of theta, you have to do this whole arc sine thing. So it can be fairly complicated, not going to lie to you. But I want to stop here because I want to show us what happens when we plug in. If we plug in the square root of 4 minus x squared, if we plug it in here, here for y, what you have is arc sine of 1. Okay, well, for arc sine of 1, when theta is 90 degrees or pi over 2, sine of theta is 1, so then arc sine of 1 is that pi over 2. So they have that inverse relationship. So you're going to get 8, 0 to 2. So that's going to be pi over 2. So this gets me pi over 4 minus x squared. Now, when this is 4 minus x squared, you have sorry. I was overthinking this. If you plug in 4 minus x squared here, you end up with 4 minus x squared, 4 minus x squared minus the square root of 4 minus x squared. So this actually comes out to 0. So that actually goes away. And then when you plug in 0 here, arc sine of 0 is 0. Sine of 0 is 0. So arc sine of 0 is 0. So arc sine has that nice piece where at 0, sine and arc sine are the same value. And then when you plug in 0 here, that goes away. So at the end of the day, all you have is this piece. So if we pull that out, you end up with 2 pi, 0 to 2, 4 minus x squared dx. which is 2 pi 4x minus 1/3 x cubed from 0 to 2 pi 8 minus 8 over 3. So let's pull an 8 out. We end up with 16 pi 1 minus 1/3. 16 pi times 2/3 is 32/3 pi, which gets us the same as this. Now, again, this is a lot longer of a path, but the whole point is to try to emphasize that we know how to get the volume of a sphere. So let's practice this method on something that's easy to verify that we've done it correctly. So you can stop watching here if you want to, because this part's over, but I want to talk to you just a little bit about why this is important. When you are learning to do something new, it is important that you, and especially a new method, it is important that you practice the method on something that you have a very clear understanding about what your answer is going to be. This is called a validation effort. And so you are trying to say, okay, this way is going to produce this thing. And so by picking something that's easy to verify that you've done it one way, you can do it the harder way. So a lot of people ask, okay, well, why should I do things the hard way? You know, why can't I do it the shortcut or whatever? It's because sometimes you can't do it the shortcut way. And so if you practice the hard way on something that you can verify with the shortcut way, then when you get to the part where you can only do the hard thing, you have it with you. So I'm just trying to emphasize and motivate you that this is not for nothing. There's a lot of this that you're going to need. And if you can't do it here, you're definitely not going to do it when you get in deeper waters.